All right, welcome back to lab, everyone. So today's lab is going to be about the index of refraction. So a long time ago, i.e. the beginning of the semester, when we talked about waves, we said that when a wave encounters a boundary, so if this is my boundary, then the wave, pardon me, which is coming in, ends up doing one of two things, actually typically both things. So part of the wave, in this case, will be reflected. So it gets reflected off in this direction. And then another part of the wave is going to be refracted, or passes through the boundary or past the boundary and then into another type of medium. So basically what's happening here is I have medium number 1 on this side. And then on this side, I have medium number 2. Now, since this happens with any wave, it turns out that electromagnetic radiation, i.e. light, is also a wave. So what's going to happen with light then is light is also going to reflect and refract when it encounters some sort of boundary. So what we're playing with in this lab is how it actually does that. So let's kind of go through this a little bit quickly. So it turns out that when light comes in incident to some sort of boundary, the angle parallel, or let's see, arrow relative to the normal here. So the normal line here, so that this is at a 90-degree angle. So this is our normal line. So the angle of incidence here, so let's call that angle of incidence. Then the angle of reflection, so let's call that theta r. So it turns out that by the law of reflections, which is done by experimental proof, so the law of reflection says that the angle of incidence is simply equal to the angle of reflection. Pardon me. So when this light comes in and encounters the boundary, gets reflected off, turns out that whatever the initial angle was relative to the vertical here, or to the normal, gets reflected back off at exactly that same amount of angle. Now, this is also true for any curved type surface. So here I try to draw this relatively straight. But if it's a curved surface, or even if it's a bumpy surface, it's always going to reflect off at exactly the same angle relative to some sort of local straight line portion. So as long as it gets reflected back into the same medium, the angle of incidence is equal to the angle of reflection. Now, for the refracted part is going to be a little bit difficult. So here I have the angle of reflection coming in. If I have another normal line going then into the second medium, this is going to come off at a different angle. Let's call that theta 2. Now, how theta incidence relates to theta 2 is all going to depend on how these two mediums are actually related to each other. So it turns out that when light travels inside of a medium, the speed of light actually slows down from that of the speed of light. So it turns out that within some sort of medium, so within a medium, more particularly in some sort of dielectric medium, what happens then is that the speed of light decreases and becomes some sort of factor of the speed of light divided by n, where n is what's known as the index of refraction. This index of refraction causes the light again to actually slow down, which actually causes some interesting optical effects. So this is actually what happens when you look at a pool and you see somebody's legs look shorter than they actually are, or if you look into a glass of water and you see the straw looks like it's bent at a different angle inside of the water or inside of your soda or whatever it is that you're drinking. All of this is some sort of optical effect based on the fact that the light travels slower inside of the medium as opposed to what it does in air. So how this gets bent is the fact that medium number 1 here is going to have an index of refraction n1, while medium 2 is going to have its own index of refraction of n2. Now, the reason for this happens because if this is some sort of dielectric material, we know that the dielectric material is going to polarize, and it's going to polarize in such a way that it creates its own electric field in the opposite direction of the incoming electric field, which means that the overall net electric field decreases. So what happens in this case then is that epsilon naught, the permittivity of free space, actually increases by an amount of the dielectric constant kappa to become the dielectric constant times then epsilon naught, which is something which we call epsilon, which is the permittivity of the medium. So basically what happens is that the size of the electric field actually reduces, which then causes the electric field to travel at a slower rate. Or another way you can kind of think about this is if this is my, say, medium, my second medium, and I have a photon. A photon is the quantum particle, which actually is the particle which makes up light. Let's say here's my photon traveling in this direction. We usually call that a gamma. When it's inside of the medium, it turns out that photons actually coupled to charge. So what happens then is inside of the dielectric, we end up with a charge separation. So I end up with negative charges and positive charges, which are now separated from each other. So I create little dipoles on the inside. Well, basically what happens is that the photon is attracted to both the positive and negative charges, which ends up causing it to slow down as it moves through the medium. So if it's moving, say, in this direction initially with a velocity of that of the speed of light, once it enters inside of the medium, it then starts to be pulled towards these charges, which means that the photon ends up acting as if it has a mass to it. So while it's inside of the dielectric medium, the mass of the photon, which initially is equal to 0, goes to something which is not 0, which means that it actually starts moving as if it is a particle feeling a viscosity or a drag force acting onto it, acting as if it has a mass. So this mass causes it to actually move slower than the speed of light. So as I showed on the other slide, it turns out that the speed of the photon inside of then the dielectric is then equal to the speed of light divided by then the index of refraction, which means the index of refraction then is simply equal to the speed of light divided then by the speed at which it's moving inside of the medium. So what this means then is that in general, the index of refraction will always be greater than 1, and it's only equal to 1 when it's actually in air or vacuum. Now, technically, even when it's inside of air, it's a little bit lower than what it is in vacuum. So in air, it's actually something like 1.001, where in air, it's actually 1. So in vacuum, it's 1. But technically, all this means is that since it's always moving slower inside of the dielectric than that of the speed of light, then the index of refraction will always then be greater than 1. So it turns out that we can actually get photons to move at a ridiculously slow rate inside of some sort of dielectric. So you can actually tune the dielectric, especially if it's a nonlinear dielectric. You can get the photon moving down to only a few centimeters per second, which is actually very slow since light travels in general at the speed c, which is about 3 × 10⁸ meters per second. So yeah, so basically what happens is, again, this is going to come in, part of it's going to be reflected off, some of it's going to be refracted, and then the relationship between the incoming angle and the refracted angle is going to be determined by these index refractions. So the way that this works is given by what's known as Snell's law. So what Snell's law says is, if this again is my boundary, and this is my incoming light, and then this is my refracted ray coming through. So my light is moving in this direction, and here it's moving in this direction. So what Snell's law actually says is if here's my normal is going through, if I can actually draw straight, there we go, on that side. And then this is my incidence angle, I'm going to call that simply θ1, and this is my refracted angle, let's call that θ2, where this is index of refraction n1, and this is index of refraction n2. What Snell's law says is that index of refraction n1 times sine of the angle θ1, where this is the angle relative to the normal, not to the horizontal, is then equal to index of refraction n2 times sine of θ2. Okay. So what this says then is that how this thing is going to be bent, either it's going to be bent toward or away from the normal, is going to depend on effectively the sizes of each one of these index refractions. So what do I mean by that? Well, let's look at the ratio of the index refractions. So let's look at n1 to n2 then is equal to, in this case, going to be sine θ2 divided by sine of θ1. So let's say that my object goes from a high index refraction down to a low index refraction. So let's look at case 1. So case 1 is that it goes from high to low. So high to low means that n1 then must be bigger than n2, Okay. Now, if n1 is greater than n2, that means this ratio of n1 divided by n2 then must be bigger than 1, right? Because I have a large number on top divided by a small number, which means it's an even bigger number. So this has to be greater than 1. So that means then that what? To have this bigger than 1, what has to be true then is what? So we know sine of 90 is equal to 1. So basically what? To get this thing to be greater than 1, so what I want is sine theta 1 sine theta 2 divided by sine of theta 1 to also be bigger than 1, which means that, let's go over here, I want sine of theta 2 to be bigger than sine of theta 1, which means that theta 2 then must be bigger than theta 1. So that means that if n-x refraction n1 is greater than n2, meaning I go from a high n-x refraction down to a low n-x refraction, theta 2 must be greater than theta 1. So what that means then is what? This thing has to bend away from the normal, which means that if it goes through a high n-x refraction to a low n-x refraction, it's going to bend away from the normal and go closer to the horizontal line. As opposed to case 2, in this case, let's say that n2 is greater than n1, meaning it's going to go from a low n-x refraction to a high n-x refraction. So I'm going to go from low to high in this case, meaning that n1 divided by n2 is going to be less than 1. Well, for n2 to be n1 over n2 to be less than 1, I then have to have, that's what, sine of theta 2 divided by sine of theta 1 is also less than 1, which means that sine of theta 2 is then less than sine of theta 1, which means that theta 2 must then be less than theta 1. So in this case, if I go from a low n-x refraction to a high n-x refraction, it has to then bend towards the normal. So in this case, this guy has to bend towards the normal. And in the previous case, this thing had to bend away from the normal. Good. So this is what Snell's law says. So again, Snell's law says how this light is actually bent is dependent on how these two n-x refractions compare to each other. So again, if I go from a high n-x refraction to a low n-x refraction, for example, if I go from water to air, in this case, the ray, which comes through the water, then is going to be bent away from the normal or closer to the horizontal as the light comes out, which then gives us that optical effect that we talked about earlier. Or if I go from low n-x refraction to a high n-x refraction, meaning if my light goes from water or from air into water, because water has a higher n-x refraction, in that case, it's going to be bent towards the normal. So how we see these things all goes back to what's called ray tracing, but I'm not going to bother going through ray tracing. We'll talk about that in class. But basically, our eye is just stupid and it follows things in a straight line. That's basically what ray tracing is. So that's what we're going to be playing with in this lab. So in this lab, we're going to be testing this idea of Snell's law. So how we're going to do that is, since you all know I'm not going to be there this week because I have to be quarantined. So basically, we're going to use this PHYS simulation. So basically, we're going to use the bending of light PHYS simulation. So basically, what you're going to have here is this guy. Okay, so here we're going to work with material 1 on the outside is going to be air. Material 2 is then going to be water. So here there's a laser, so we can turn on this laser, and then here you see the incoming light, the reflected light, and then the refracted light. Okay, so good. So here we're simply going to take the protractor. So take our protractor, and then we're going to put that over on here so that it is aligned with the normal. And then here we're going to measure this for different angles. So initially we're going to put this at 30 degrees. So we have the incoming light at 30 degrees. So this is 30 degrees from the normal line. And then from here, you're going to measure then the refracted beam. Okay. And then you're going to go ahead and move that to 40 degrees. So now let's put it at 40 degrees, do the same thing, measure the refracted beam, and then also put it at 50 degrees. And then measure the refracted beam. Now, from here, you'll then use Snell's law across the boundary. So here, air, as this thing says, has an n-x refraction of n1. So you're going to have sine n1, so 1 times sine of theta 1, which is this initial angle. So let's call that 50 degrees. Then is equal to n2 Now here, it tells you what N2 is, but we're gonna use N2 as our unknown. So write just simply N2 times sine of theta 2, where theta 2 is whatever this angle it is that I'm measuring here, which looks like about 35 degrees. It might be 34, maybe 33, but let's call it about 35. So here, I'm gonna write that down that I have sine of 50 degrees then is equal to, pardon me, N2 sine of 35 degrees. From there, solve for N2, do that for each one of the different angles. For each one of those, you'll get a different number for what N2 is, take an average of all of those, and then that's going to give you the inexor refraction of the water. Since this tells us we know the inexor refraction of the water is 1.33, then you can do your discrepancies, both relative and absolute discrepancies. Good. So now, for the second part, so that's part A, or part 1. Part 2 or part B, we're now going to switch to mystery A. Okay, so now let's use mystery material number A. So here we don't know what the inexor refraction is. So here we're going to do the same thing. So we're going to start off at 30 degrees, measure the refracted angle, 40 degrees, refracted angle, 50 degrees, measure the refracted angle. From there, again, use Snell's law across the boundary all 3 times, calculate the inexor refraction for each one of those. Take an average, that is the inexor refraction of this material, mystery material A. Now, we don't know what this material's inexor refraction is, so we can't use discrepancies in this case. So we just have to quote what it is and then move on from there. Now, the last part of the lab is now dealing with a prism. So here, we're going to use this particular prism. So I'm going to use this guy. Okay. So I'm going to drop that in here. And then you can rotate this guy around. Well, we want to set it up pretty much initially the way that it was. Okay. Now, from here, again, we're going to shine our laser, which we can move anywhere that we want to. I'm going to do something like this. So here's my laser. And now what we could do in this case then is we want this on glass. So we'll leave it on glass. Okay. And then here, we're going to keep off the reflections, but we're going to put on the normal lines. So here are our normal lines, just to make it a little easier. And then we're going to drag out our protractor. So here, we're going to do the same thing. So here, we're going to use our protractor to measure for this normal here, the incident angle here, and then a refracted angle here. And then on this side, this is going to be the incident angle on this side, and then this is going to be our refracted angle on this side. So basically, for each one of these normals, we're just going to rotate this guy around so it matches where the normal is, and then move it to that particular location. So this is the location I want. Let's do that. Good. So this is about where the normal is. So again, from here, I'll measure this incoming angle, measure the refracted angle here, move my protractor then to the other side. So move it over here. You might have to turn it off and then turn it back on so you can move it where you want it to, but just kind of drag it over. Anyways, so when I drag it over here, there we go. Again, do the same thing, measure the incident angle on this side, refracted angle on this side. Again, apply Snell's law across the boundary on each side to then extract what is the inexor refraction of the glass. Now, glass should be an inexor refraction of somewhere around 1.5. So you can do discrepancies based off of 1.5. I'm not quite sure what they're using for 1.5, but we can use 1.5 in this case, okay? Now, one other interesting thing is, we can actually take a look from here, is it turns out that the inexor refraction is also wavelength dependent, which basically means that different colors will travel at different velocities inside of the dielectric material. So as a nice way to see that, if I kind of drag this guy here, you can see that these angles are actually changing, right? Especially this one here. So actually, let me bring the protractor back out so you can see that a little bit better. So if I put this guy at 0 degrees here, and I gotta drag this. So again, you can see this guy getting to close to 90 degrees. And if I go all the way up to red, in this case, it's out to, what is that? So it's about 70, about 80 degrees. So you see almost 10-degree difference between the red here and the violets, right? So it turns out, as I said, that inexor refraction is actually material, or not material, it is frequency dependent, which means each one of these different frequencies has their own different index of refraction because they all move at a different velocity, right? So they all move at a different speed. Now, technically, inside of here, this thing has one index of refraction regardless of the type of material, which means then that the amount at which each one is bent should be dependent on the velocity, which means that each one of these has a different velocity inside of the material, which means they're all going to be bent differently, because what happens actually is inside of the material, light is bent to minimize the amount of time at which it spends inside of the material. This is what's known as Fermat's principle. So one thing you can do, you don't have to do this, I'm not going to grade this part, but just for funsies, is you can play with different frequencies here and apply Snell's law for different frequencies and see that you actually get the same answer based on the fact that these guys are actually bent at different angles. So anyways, just a nice fun thing that you can actually play with. Again, that's not actually part of the lab, so you don't actually have to do that. But again, just to recap, you are doing the three things. So here we're doing the prism. You are doing for water and for mystery material A. Okay. So again, we're doing these labs a little bit out of sequence. So we're doing this one before we do the induction lab, just because I won't be able to come in this week, at least for the first part of the week, and we'll see what happens for the rest of the week. And then we'll do in class next week, we'll do the EMF lab. Okay, so the induction lab. All right, so that's it. So let me know if you have any questions, and I'll see you all then next week.